Hi folks, welcome to our Understanding Axial Stress series, and today we are looking at chapter 8, which relates to variable axial loader. So this is the content that's been covered today. So we start off by looking at fundamental failure in engineering components or engineering materials in that context. Then we moved on to look at direct stress and strain. And we also had a look at the Young's modulus and the strain energy. So the strain energy, as a reminder, is the amount of energy required in causing deformation in material. So whether that is due to an external or internal stimulus, that's fundamentally what strain energy quantifies. So hopefully down the line, we are going to look at a simple experiment to bring everything full circle in terms of how the Young's modulus is proven relating to various engineering material. So that's something that we will be looking forward to looking at. So following that, we looked at thermal load. So what happens when a component experiences some form of temperature differential? Will that instigate some measure of deformation within engineering component, and should that be something that as designers need to be quantified when we are analyzing deformation in engineering components? We also looked at the concept of compactability. So this is where if we have a situation of indeterminacy, how do we go about working through those problems by establishing equations to enable us to predict what the stresses are within an engineering component? We also looked at some fundamentals relating to shear stress, and from there we also looked at the concept of the safety factor, or the factor of safety. So hopefully you've already watched these videos. If you've not, please make it a point to watch these videos to give you a better understanding in terms of what we're talking about in terms of unit axial stress. So today we are going to be looking at the concept of variable loading in engineering components. So let's look at a situation whereby, unlike the previous examples where we looked at a component being subjected to some form of tensile load, we have a situation whereby we've got a series of loads acting on segments of a component. So in this particular problem, we are being challenged to calculate the axial deflection in each section of the given step bar. And from there, we're also being tasked to calculate what the resultant axial deflection or extension or reduction length will be in this particular product or component. So in terms of this problem, we've got 3 external loads and there's one that's unknown, and we need to establish whether this unknown force to cause equilibrium in this component will be either in tension or in compression. So we've been given a tensile load of 10 kilograms. So let's say that is section A. Section B is being subjected to 2 forces. So we've got a compressive load of 15 kilonewtons, and we have another compressive load acting on the opposite face of the component, which measures 7 kilonewtons. And we need to use this information to calculate what will be this 4th load, which will cause static equilibrium on the loading on the given component. So that's essentially what our challenge is. The question is, how do we go about solving this particular problem? For us to solve this problem, we need to figure out what the internal forces are within the structure. So what normally happens is, when you apply a force, an external stimulus or stimuli on the particular on the given component or material, for the material to resist deformation, it has to develop some measure of internal loading to counteract the external load that's causing it to deform to be in equilibrium. So since section A, or let's call that section AB, is being subjected to a force 10 kilonewtons, then it needs to generate some form of internal reaction which will counter that tensile load. Thus, that reaction will be equal in magnitude but opposite in sense or direction. So we've got a 10 kilonewton force acting on the surface of section AB. Thus, to keep the component in equilibrium, okay, with respect to Newton's third law, then the material has to generate a reaction which will be of a similar magnitude 10 kilonewtons, but it will be compressive. So the internal load experienced within the component, section AB, will be in compression. When we come to BC, this is where we have two forces that's causing compression on section BC. Thus, internally, BC needs to generate an internal force to counteract the loading acting on its surface. So the internal load in this case will be in tension to cause section BC to be in equilibrium with respect to the external stimulus causing deformation to it. And similarly, section DC, we are speculating that it will be subjected to some form of external tensile load, characterized by the unknown force F subscript 4 in our case, or the unknown force. So we are speculating that this will be the case. So that the external loader will be in compression to counteract the external load, which is in tension. So now that we know that, how do we go about calculating or predicting what the internal forces are in each section of the step bar? Alright folks, so let's go through this problem related to how we go about determining the internal loading in the components in that given problem. So we've got section AB. We know that there is a tensor force that's acting on the component for that particular section. So for the material to be in a state of equilibrium, the material needs to generate an internal force to counter the applied tensile force at that particular cross section. Thus, the force acting at the interface A will be 10 newtons. But since that's going to counter, that's going to be a compressive load. That's what more or less inferred. The internal force, the internal loading will be compressive to counter or to balance the force at the intersection there. Okay, so that will also be 10 kilonewtons. So for the load diagram, since the force is going to be compressive, then what we will do is we are going to draw a line projected from the zero line downwards. And again, if you're going to do this graphically, it might be worth using a reasonable scale. Alright, so that would be 10 kilonewtons. So I'm going to assume that is 10 kilonewtons. Okay, so we can write 10 there, minus 10. So that below the line is negative, above the line is positive. We're also going to assume that since there aren't any forces countering the 10 kilonewton force across this sectional profile of AB, then we're going to assume that the compressive force is constant along that until we get to interface B, where we've got the 15 kilonewton force. So we're going to draw a projection from interface B. Alright, so that is, let's call that A. Yeah. Let's call this B. So as I stated, we're more or less going to assume that to be constant until we get to interface B, where we have the 15 kilonewton force. So as a result of that, we need to work out what the net force is going to be. So the net force at this point will be minus 10 plus 15. Because within the material, even though you've got an external compressive force of 15, the material needs to generate a reaction to counter the compressive load, so that reaction will be in tension. Okay. So the net force will be 5 kilonewtons. So we go 15, so this is 10, so we need to add plus 5. So this is the difference there. So that difference gives us our net internal force. So this would be 5. Okay, so similar to section AB, we are going to have a situation whereby within the material, that internal force will be consistent through the section until we get to the surface of BC, moving into CD. Okay, so we are going to assume that that force there, so this tensor force there, 5, is uniform throughout until we get to the interface of C, where we now have another force that's going to cause the material to generate a counter reaction. So we've got 7 newtons, so 7 newtons is compressing that surface, so that means that the material needs to generate a counter to that. So that counter will be minus 7 newtons. So that net between 5 and 7 will leave minus 2. All right, so the force is going to come down. So we've got 5 and we have 2. As I stated, it might be worth doing this to scale. So use a reasonable scale to plot this graph. So as usual, we're going to have a situation whereby, since there are no forces countering the minus 2 Newton force in here, to balance this out to 0, there has to be a counter force of 2. So the external force to counter that compressive force from minus 2 needs to equate to 2. So we need to project from minus 2 back to the 0 line to ensure that the force system, internal force system within the component is in equilibrium. Okay. Thus, we're going to project back to the 0 line. And this is what we're going to have. So this bit there relates to the net force. So the net force there, which will represent the internal force, will be 5 minus 7, which will be equal to minus 2 Kn. Okay. So we are assuming that the external force here, in terms of the components, this will equate to 2 kilonewtons. So force F stands for 4 is 2 kilonewtons. And we can use the equations of equilibrium, as I like to call it, to work out what the balancing forces are to depict what minus F4 is. And if you work it out, you realize that you get a force of 2. So the tensile force that needs to be applied to the component to keep it in equilibrium will be 2 kilonewtons. And this, ladies and gentlemen, gives us the force diagram, or the load diagram. Okay. So for section A, B, this is minus 10. Let's use the red pen. This will be minus 10 kilonewtons. For section BC, that will be 5 kilonewtons. And for section CD, that will be minus 2 kilonewtons. And these are the internal forces in the material. It's about deducing what the internal loadings are for, or the internal loading is for each section of the bar. We can now use the graphic technique in determining what the measure of the forces are in each section of the bar. So as demonstrated, at section A, there is a tensile force of 10 kilonewtons, thus there will be a compression force acting to counteract that force to ensure that that section of the component is in equilibrium. Okay, so since there isn't any forces along the cross-sectional profile of AB, we are going to assume that that force is constant throughout until we get to interface B, where we have the 15 Newton force acting to counteract the 10 Newton force. So the net force we'll create the tensor load that we pointed out. So that tensor load will be 5 kilonewtons. So that will be the difference between 10 kilonewtons and 15 kilonewtons. Okay, so because that is more or less going to be positive, that more or less indicates that the measure of the internal force within that section of the component will be in tension. So we are more or less assuming that throughout the cross-sectional profile of section BC, there won't be any change to the 5 kilonewton force. So when we get to interface C, we've got the 7 Newton force there, and the net difference will be minus 2 kilonewtons, which indicates that the cross-sectional profile of the component, so section CD, will be in compression. Thus, to bring a balance in terms of the forces acting on the component, this indicates that for it to be in equilibrium, then it has to be a countermeasure of 2 kilonewtons to bring everything back to 0. Thus, the sum of the forces within the component should sum up to 0. Okay, and there we have it. So again, we can use the concept of the equations of equilibrium to prove that. So the sum of the forces in X, we are going to assume that the sum of all the forces will equate to 0. Thus, F1 plus F2 plus F3 plus F4 should all sum up to give us 0. Thus, making F4 the subject of this relationship, this would give us minus into bracket F1 plus F2 plus F3. Okay. So, to ensure that we don't have any confusion, we are going to determine the census of the forces in terms of the direction. So forces moving rightwards, we will assume to be positive. Forces moving leftwards, we assume to be negative. Okay, so compressive forces will have a negative sense, tensile forces will have a positive sense. Thus, into bracket minus 10 plus 15 plus into bracket minus 7, all brackets closed. So that would give a sum of minus 2. So minus times minus 2 gives positive 2. Thus, F4 will be equal to 2 kilonewton. So the mass kind of like makes sense here, and it does justify the rationale behind the load diagram, which was just used to determine the forces within each component, each section, of the given component. So section AB has an internal force of minus 10 kilonewtons. Section BC has a net force of 5 kilonewtons, or an internal force of 5 kilonewtons, and section CD has a net force of minus 2 kilonewtons. So we can then proceed to calculate the cross-sectional profile. So since the component is circular, we can use pi r squared if you want to calculate what the cross-sectional area is, or we can use pi d squared over 4 to do likewise. So section AB will yield a sectional area of 1256.64. BC yields a cross-sectional area of 2827.43, and section CD will give a cross-sectional area when calculated at 314.16. So we know what the sectional area is, we know what the internal loadings are, so we can then proceed to calculate what the individual deflections are within each section of the given component. So this is a very quick sample calculation in terms of what we need to do. So we've already talked about how to go about calculating the cross-sectional area. So at this point in time, we should be familiar with the engineer's equation when it comes to calculating the area of a circle. Okay, so as I've more or less pointed out previously, we calculate the sectional area for each segment of the given bar. So for section AB will be equal to pi over 4 times the diameter with respect to section AB squared, and that gives 1256.64 millimeters squared. So to calculate the deflection, this is the equation that we are going to be using. So to calculate the deflection, and this equation comes from the stress-strain equation when combined. So this is equal to N. So N characterizes the internal load within the component. L characterizes the length of that particular section, divided by A times E. So A is the sectional area and E is the modulus of resilience, aka the Young's modulus. So by putting in the known information or the known data that we have, so N 10,000 minus 10,000, so again don't forget the sense of the forces that we're using. The length is 30 millimeters, divided by the product of the area, which is 1256.64, times the Young's modulus for that particular section. So that particular section, the Young's modulus is given as 200 GPa, but in terms of the basis of millimeters, that'll be 200 kilonewton per millimeter squared. Okay, so they more or less mean the same thing. So once we do the needed computation, we get a value of minus 1.1937 times 10 to the power minus 3 millimeters. So that is the deflection, or the measure of extension within that particular section of the component. So as pointed out previously, this is the equation that I just showed you quite briefly. So the axial deflection, delta, is equal to NL over AE. So N is the internal force or the internal load within the component, L is the length of the component, A is the cross section, and E is the Young's modulus for that particular material. So if you have a situation whereby the component is constituted of different materials, thus making it some form of composite, then for a given section or a component with different sectional profiles, then you need to know what the Young's modulus of each profile will be. Fortunately for this particular problem, the material is homogeneously fabricated out of one material. So E is constant throughout the section of the step bar. So the total deflection will be the sum of the individual deflections of each section of the step bar. So what we need to do is we need to calculate what the deflection is for section AB for the component, plus the deflection of section BC, plus the deflection of section CD. And this is what is represented in the table below. The cross section of each component in terms of the area, thus using area is equal to pi over 4 times d squared. So we've already more or less looked at how that is calculated. We've also noted down what the internal forces are for each section of the step bar. So section AB is minus 10 kilonewtons, section BC is 5 kilonewtons, and section CD is minus 2. If we've already been given some geometric data relating to the length of each section, so section AB is 30 millimeters, section BC is 20, and section CD is 50. And as I stated, because the material is homogeneous throughout, the elastic modulus will be the same. So thus 200 GPa. So if you're working the basis of meters, but if you're working the basis of millimeters, then that needs to be converted to kilonewton per millimeter squared. So using the deflection equation, the axial deflection equation, these are the results that we obtain. So for section AB, the deflection equated to minus 1.1937 times 10 to the power minus 3 millimeters. Section BC, gave a net result of 1.7684 times 10 to the power minus 4 millimeters. And section CD gave an axial deflection of minus 1.5916 times 10 to the power minus 3 millimeters. So the sum of all the deflections experienced per section of the step bar yielded minus 2.6085 times 10 to the power minus 3 millimeters. And there we have it. Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.